Welcome to Mech Cosmos, Engineering Explained. On the 1st of June 2009, Air France Flight 447 departed Rio de Janeiro Galeão International Airport at 19:03 local time. On board were 228 people, 216 passengers and 12 crew members. The aircraft was an Airbus A330-200, one of the most modern and sophisticated passenger jets in the world at that time. The flight to Paris Charles de Gaulle was scheduled to take approximately 11 hours. It was a routine overnight transatlantic crossing that Air France operated multiple times every week. The crew was experienced. The aircraft was in perfect technical condition. It had been inspected and certified airworthy before departure. There was absolutely no reason to expect anything other than a completely normal flight. 3 hours and 37 minutes after takeoff, the aircraft disappeared from radar over the Atlantic Ocean. There was no distress call, no emergency signal, no warning of any kind. Air France Flight 447 had simply vanished from the screens of air traffic controllers in the middle of the night over one of the most remote stretches of ocean on Earth. It would take 5 days of searching before the first pieces of wreckage and the first bodies were found floating on the surface of the Atlantic. It would take nearly 2 years to locate the main wreckage on the ocean floor. It would take another year to recover the flight recorders from the depths. And when investigators finally pieced together exactly what had happened in the final 4 minutes and 23 seconds of that flight, the findings shocked the entire aviation world and changed the way pilots are trained forever. This was not a story of a catastrophic mechanical failure. This was not a story of a bomb or a terrorist attack. This was not a story of a fundamental design flaw that made the aircraft unflyable. This was a story of how a series of small failures cascaded into a disaster. How a temporary sensor malfunction lasting less than 1 minute confused experienced pilots. How the automation they relied on every day suddenly disappeared, leaving them alone with an aircraft they did not fully understand how to fly manually. How 3 experienced pilots in a modern cockpit could not diagnose a situation that in hindsight seemed straightforward. And how 228 people died, not because the aircraft broke beyond recovery, but because the humans flying it lost control of a perfectly flyable machine. This is the complete engineering and human factors explanation of the Air France 447 disaster. We are Mech Cosmos. Engineering. Explained. Let us begin. To understand what happened to Flight 447, you first need to understand the aircraft and how modern fly-by-wire automation systems work, because the automation is central to this story. The Airbus A330 is a wide-body twin-engine long-haul jet aircraft that entered service in 1994. By 2009, it was a mature, well-proven design with an excellent safety record. Like all Airbus aircraft, it uses a fly-by-wire flight control system. In a conventional aircraft, the pilot moves the control column, and the movement is transmitted mechanically or hydraulically to the control surfaces. The ailerons that roll the elevators that control pitch, and the rudder that controls yaw. The pilot feels resistance in the controls. They can sense the aerodynamic loads on the surfaces. There is a direct physical connection between the pilot and the aircraft. In a fly-by-wire aircraft, this physical connection does not exist. The pilot's control inputs are converted into electrical signals. These signals are sent to flight control computers. The computers calculate the appropriate deflection of the control surfaces and command them through electrical actuators. There is no mechanical linkage. The pilot is not directly flying the aircraft. They are telling the computers what they want the aircraft to do, and the computers make it happen. The Airbus fly-by-wire system uses side sticks instead of traditional control columns. A side stick is a small joystick mounted on the side console to the left of the captain and to the right of the first officer. Moving the side stick commands a flight path. Push forward, and the nose pitches down. Pull back, and the nose pitches up. Move left or right, and the aircraft banks. The side stick is small and light. It requires very little force to operate. And critically, it does not move when the autopilot is flying. It sits in its neutral rest position, regardless of what the autopilot is commanding the aircraft to do. This means that when the autopilot is engaged, the pilot has no physical feedback about the aircraft's attitude or control surface positions through the side stick. In normal law, the normal operating mode of the Airbus fly-by-wire system, the computers provide comprehensive envelope protection. The pilot cannot stall the aircraft. If the pilot pulls the side stick fully back, the computers will not allow the angle of attack to exceed the stall angle. The pilot cannot overstress the airframe. The computers will not allow a bank angle greater than 67 degrees in normal maneuvering. The pilot cannot exceed the aircraft's maximum speed or dive limits. The computers enforce all of these limits automatically, regardless of what the pilot commands. The pilot simply cannot break the aircraft in normal law. This system makes the aircraft extremely safe in routine operations and has contributed significantly to the outstanding safety record of fly-by-wire Airbus aircraft. But this protection has a consequence that proved absolutely critical on the night of June 1, 2009. Pilots flying in normal law never experience a stall. They never feel the buffeting that precedes a stall. They never experience the nose drop and loss of lift that characterizes a full aerodynamic stall. The computers will not allow it. Over years of flying, these aircraft pilots can lose familiarity with stall recognition and stall recovery. They fly the automation. They do not fly the aircraft directly. And if the automation ever fails or reverts to a degraded mode, the pilots may find themselves flying an aircraft that behaves very differently from anything they have practiced. The crew of Flight 447 on that night in June 2009 consisted of 3 pilots, as is normal on long-haul flights. The captain was Marc Dubois. He was 58 years old and had accumulated over 11,000 flying hours, of which 1,700 were on the Airbus A330. He was an experienced and respected pilot. On long-haul flights, it is normal and legally permitted for the captain to take a rest period during the cruise phase. Captain Dubois went to the crew rest area to sleep approximately 90 minutes before the critical events. The aircraft was left in the care of the 2 co-pilots. The co-pilot in the right seat, the pilot flying position, was Pierre-Cédric Bonin. He was 32 years old with approximately 2,900 total flying hours, of which around 800 were on the A330. He was the least experienced of the 3 pilots. The co-pilot in the left seat, the pilot monitoring position, was David Robert. He was 37 years old with approximately 6,600 total flying hours and significantly more experience than Bonin. Robert was acting as the senior pilot on the flight deck during the captain's rest period. The flight proceeded completely normally for the first 3.5 hours. The aircraft climbed to its cruising altitude of flight level 350, 35,000 feet, and the autopilot and autothrust maintained cruise flight. The crew monitored systems, communicated with air traffic control, and performed their normal duties. The weather ahead showed areas of convective activity, thunderstorm cells, which is common in the intertropical convergence zone over the equatorial Atlantic. This area is one of the most meteorologically active regions on Earth. Large, powerful thunderstorm cells develop rapidly and can extend to extreme altitudes. Other aircraft in the area that night were deviating around the most intense cells. The crew discussed the weather. They reduced speed slightly as a precautionary measure in anticipation of turbulence. They made some lateral adjustments to their route, but they continued into an area of significant convective weather. At approximately 2 UTC, 1 hour before their scheduled crossing of the equator, the aircraft entered an area of turbulence associated with the weather system. At 0206 UTC, a cascade of events began that would end the flight. The Pitot tubes, the small forward-facing probes mounted on the fuselage of the aircraft that measure airspeed by sensing the pressure difference between the stagnant air in the tube and the static air pressure, became blocked by ice crystals. Pitot tube icing is a known phenomenon. At high altitude in convective weather, supercooled water droplets and ice crystals can accumulate on and inside the Pitot tube faster than the electrical heating elements can evaporate them. When this happens, the tube becomes blocked and the pressure reading becomes unreliable or frozen. The A330 has 3 Pitot probes. They feed airspeed information to 3 separate air data systems. When the Pitot tubes became blocked, the 3 systems began giving different and inconsistent airspeed readings. The flight computers detected these inconsistencies and could no longer determine a reliable airspeed. This triggered automatic disconnection of the autopilot and autothrust systems. The aircraft reverted from normal law to alternate law, a degraded control mode in which some envelope protections, including crucially the angle of attack protection against stall, are no longer active. The transition from normal law to alternate law is significant. In alternate law, the aircraft can be stalled. The computers will no longer prevent it. But the crew was not explicitly warned that they were now in alternate law. The mode change was indicated on the flight displays, but in the confusion of the moment, with multiple alarms sounding and the aircraft suddenly requiring manual flying, after hours of automated cruise, this information was not registered or acted upon. The autopilot disconnection triggered an alarm. The aircraft began to roll slightly to the right in the turbulence. Co-pilot Bonin in the right seat took manual control of the aircraft, and in the next few seconds he made the input that sealed the fate of everyone on board. Bonin pulled back on his side stick. He raised the nose of the aircraft significantly. The nose pitched up. The aircraft began to climb. This was the wrong input. The correct procedure when facing unreliable airspeed at cruise altitude is well defined. Maintain the existing pitch attitude. Maintain the existing thrust setting. Do not make large control inputs. Wait for the situation to stabilize. The aircraft was flying perfectly normally. The Pitot icing was a temporary condition. Within approximately 1 minute, the ice cleared and the Pitot tubes returned to normal function, providing accurate airspeed again. If the crew had simply maintained the existing configuration, the aircraft would have continued flying normally, and the Pitot icing would have been a minor incident logged in the maintenance records. Instead, Bonin raised the nose to approximately 11 degrees nose-up attitude. The aircraft climbed rapidly from 35,000 feet. As it climbed, the airspeed decreased. As the airspeed decreased and the nose remained high, the angle of attack, the angle between the chord line of the wing and the direction of the oncoming air, increased. At a certain critical angle of attack, the smooth airflow over the upper surface of the wing separates. The wing loses the ability to generate lift. This is an aerodynamic stall. The stall warning activated. A loud repeating synthetic voice called the cricket began calling stall, stall, stall. It sounded for approximately 5 seconds. Then it stopped. The reason it stopped was deeply confusing and ultimately contributed to the crew's failure to recognize the situation. The stall warning system on the A330 has a logic that inhibits the warning when the computed airspeed drops below a certain threshold, because at very low speeds, the angle of attack data is considered unreliable. The airspeed indications had dropped to very low values because of the Pitot tube blockage. The computers therefore inhibited the stall warning, assuming it must be a false alarm caused by the unreliable airspeed data. This created a situation where the stall warning sounded briefly when the aircraft first entered the stall and then went silent, giving the crew the false impression that the stall condition had resolved, when in reality it had not. The aircraft continued to climb. It reached an altitude of 38,000 feet, well above its certified maximum operating altitude. At this extreme altitude, the air is very thin. The margins between the minimum speed needed to maintain lift and the maximum speed permitted by the aircraft's structural limits are very narrow. This narrow band is called the coffin corner. At this altitude, any disturbance or incorrect control input could quickly lead to a stall. The aircraft then began to descend. With its wings stalled, it was generating very little lift. The nose was still pointed slightly upward, but the aircraft was descending at an increasing rate. The airspeed indications were still unreliable and showing inconsistent values on the different displays. The attitude indicators showed the nose-up attitude, but the altimeter showed the aircraft was descending rapidly. The vertical speed indicator showed a descent rate that was increasing toward thousands of feet per minute. Co-pilot Robert in the left seat was trying desperately to understand what was happening. He called for the captain. At 02:11 UTC, approximately 90 seconds after the autopilot disconnected, Captain Dubois arrived on the flight deck. He had been asleep. He was woken by the turbulence and the alarms and arrived still disoriented from his interrupted sleep. He assessed the situation but could not quickly determine what had gone wrong. The instruments were showing confusing information. The airspeed indications were partially recovered by this point, but the values were still not fully reliable. The fundamental problem was that none of the three pilots correctly diagnosed that the aircraft was in a stall. A stall at cruise altitude in a large transport aircraft was so far outside their experience and expectation that it did not register as the correct diagnosis. Bonin continued to hold back pressure on his side stick for most of the remaining flight. He was pulling the nose up. But pulling the nose up in a stall makes the stall worse. It increases the angle of attack, it deepens the stall. The correct recovery action, push the nose forward to reduce angle of attack, is deeply counterintuitive when the aircraft is already descending at high speed toward the ocean. The non-linked side stick design meant that Robert could not feel what Bonin was doing. When Robert made forward inputs on his own side stick to try to lower the nose, these inputs were partially cancelled by Bonin's simultaneous backward inputs. The computers summed the two inputs. Neither pilot was aware of what the other was doing with their side stick. At one critical moment, Robert announced he had the controls and pushed forward. The aircraft responded. The descent rate decreased. The angle of attack began to drop. For a brief moment, recovery was within reach. But Bonin took back the controls almost immediately and pulled again. The recovery was abandoned. The aircraft returned to its fully stalled condition. The stall warning activated again briefly near the end of the flight, when the airspeed indications had recovered sufficiently for the warning logic to become active again. But by this point, the aircraft was at very low altitude, descending at extreme speed, and there was no time to recover. At 02:14 UTC, exactly 4 minutes and 23 seconds after the autopilot disconnected, Air France Flight 447 struck the surface of the Atlantic Ocean. The vertical speed at impact was approximately 2,900 feet per minute. The aircraft was in a slight nose-up attitude at the moment of impact. The impact forces were unsurvivable. The aircraft disintegrated on contact with the water. All 228 people on board died instantly. The search for the aircraft began immediately. Air France diverted other aircraft to the area. The Brazilian and French navies deployed ships. Within 5 days, the first floating debris and the first bodies were recovered from the surface. But the main wreckage and the flight recorders were on the ocean floor, and finding them would prove extraordinarily difficult. The Atlantic Ocean in the area where Flight 447 went down is not flat. The seafloor in that region is part of the Mid-Atlantic Ridge, a volcanic mountain range running the length of the Atlantic. The terrain is extremely rugged with mountains, valleys, and deep chasms. The water depth in the search area ranges from 1,000 to over 4,000 meters. The search area was enormous. Based on the last radar contact and the estimated drift of floating debris, the main wreckage could be anywhere within an area of thousands of square kilometers. 3 separate underwater search campaigns were conducted using specialized deep-sea search vessels equipped with sonar and remotely operated vehicles. The first 2 campaigns in 2009 and 2010 failed to find the main wreckage despite covering large areas of the seafloor. The flight recorders were not found. Without the recorders, investigators could only speculate about what had happened in the final minutes. In March 2011, a 4th search was launched, using new search area calculations based on refined drift modeling of the floating debris that had been recovered from the surface. On April 3, 2011, nearly 2 years after the accident, the underwater vehicle conducting the search located the main wreckage field on the seafloor at a depth of approximately 3,900 meters. The wreckage was spread over a relatively compact area, indicating a high-energy near-vertical impact. In May 2011, remotely operated vehicles recovered the flight data recorder and the cockpit voice recorder from the wreckage. The recorders were brought to the surface and flown to Paris for analysis. The data on the recorders was intact. It provided a complete second-by-second record of every parameter of the flight, and a full audio recording of everything said on the flight deck during the final minutes. The investigation team could now reconstruct exactly what had happened. The official investigation was conducted by the Bureau d'enquête et d'analyse pour la sécurité de l'aviation civile, the BEA, the French Civil Aviation Accident Investigation Authority. The final report published in July 2012 identified the causes and contributing factors in detail. The immediate technical cause was the temporary obstruction of the Pitot tubes by ice crystals, causing the autopilot and autothrust to disconnect and triggering the transition to alternate law. The investigation found that the Thales AA Pitot tubes, fitted to many A330 aircraft, had a known higher susceptibility to icing than the alternative Goodrich Pitot tubes. Air France had been aware of this issue and had ordered the replacement of the Thales tubes with Goodrich tubes on its A330 fleet. The replacement program was underway but had not been completed. The two other Air France A330 aircraft that operated the Rio to Paris route had already received the replacement Pitot tubes. Flight 447 had not. Following the accident, Airbus and Air France immediately accelerated the replacement program, and the Thales Pitot tubes were removed from all A330 aircraft worldwide. But the investigation made clear that the Pitot tube failure alone would not have caused the accident. The icing was temporary. The Pitot tubes recovered normal function within approximately 1 minute. If the crew had maintained the correct aircraft configuration, during that 1 minute the flight would have continued normally. The accident happened because of the crew's response to the situation. The investigation identified that the crew did not apply the unreliable airspeed procedure correctly. They did not maintain a safe pitch attitude and thrust setting. They made large control inputs that destabilized the aircraft. They did not correctly identify the stall. And when the stall warning did sound, they did not execute a stall recovery. The investigation also identified deeper systemic factors that contributed to the crew's failure. Pilots of highly automated aircraft were not receiving adequate training in manual flying skills and in handling the aircraft in degraded automation states. The transition from normal law to alternate law was not sufficiently emphasized in training. Pilots were not adequately prepared to fly the aircraft manually at high altitude. The industry had allowed pilot manual flying proficiency to atrophy through over-reliance on automation. The non-linked side-stick design was also identified as a contributing factor. In a conventional aircraft with a linked control column, if one pilot pushes forward and the other pulls back, the column moves to a compromise position, and both pilots can feel what the other is doing. With independent side sticks, neither pilot has any tactile awareness of the other's inputs. The investigation recommended that Airbus review the side stick design and improve the crew alerting when both pilots are making simultaneous inputs. The consequences of the Air France 447 accident for global aviation safety were profound and far-reaching. Regulatory authorities around the world introduced new requirements for upset prevention and recovery training, UPRT, for airline pilots. This training specifically addresses the recognition and recovery from unusual attitudes and aerodynamic stalls in transport category aircraft, including practice in actual stall recovery, rather than just recovery at the first sign of an impending stall, as had previously been standard. Airlines were required to increase opportunities for pilots to practice manual flying to maintain proficiency. New procedures were introduced for handling unreliable airspeed situations. The accident also intensified a broader debate in aviation about the appropriate level of automation in modern cockpits and the skills that pilots need to maintain. The concept of automation dependency, where pilots become so reliant on automation that they lose the ability to fly effectively without it, became a central topic in aviation safety research and pilot training philosophy. The challenge of keeping human pilots skilled and effective in an increasingly automated environment remains one of the most important questions in aviation safety today. The Air France 447 accident is studied in every airline pilot training program in the world. It is analyzed in detail in crew resource management courses. It is used to illustrate the dangers of automation dependency loss, of manual flying skills, failure to follow standard operating procedures, and the critical importance of crew communication and coordination under stress. Every pilot who has trained in the years since 2009 has learned from what happened on that aircraft over the Atlantic Ocean. 228 people lost their lives on the night of June 1, 2009. Their deaths were not in vain. The investigation into Flight 447 identified real vulnerabilities in the aviation system, and real changes were made as a result. The Pitot tube issue was fixed. Pilot training was improved worldwide. Procedures were updated. The probability of a similar accident occurring today is meaningfully lower because of everything the aviation world learned from this tragedy. That is the legacy of Air France Flight 447. And that is why we study these accidents. Not to assign blame, not to sensationalize tragedy, but to understand exactly what went wrong so that we can make sure it never happens again. We are Mech Cosmos. Engineering. Explained. If this video gave you a deeper understanding of what happened to Flight 447 and why, then subscribe, hit the notification bell, and join us for the next video. Because every machine has a story, and sometimes that story teaches us how to make the world safer.